In part one, we trace the insane 60-year miracle of Moore's Law and how it's finally cracking under the brutal physics at 2 nanometers. But today, in part two, we're looking at what comes next. The new frontiers of 3D stacking, advanced packaging, photonics, and whether we can actually keep this miracle alive in completely new forms.
Holy shit, yeah. This is where it gets really interesting and honestly, a little scary.
Right. I mean, we've got this massive stack of sources today. We're talking the newly unsealed 2025 and 2026 roadmaps from Intel and TSMC.
Huge drops.
Yeah, plus Jensen Huang's keynotes, ASML photonics reports, and some incredibly dense academic papers from Spectrum and Nature. And our mission today is to figure out how human innovation is basically going to war with the immovable laws of quantum physics.
Because that's exactly what it is, a war. You can throw billions of dollars at the problem, you can hire the smartest physicists on the planet, but, you literally cannot negotiate with quantum mechanics. We have basically run out of atoms.
I was reading through the IE spectrum breakdown of the 2-nanometer node, and honestly, holy fuck, the scale we are talking about here completely breaks the human brain.
Oh, totally.
But before we get into the wild new frontiers of 3D stacking and, literal lasers on silicon, let's establish the baseline. Because for 6 decades, we've basically just been slicing the silicon pizza thinner and thinner.
Right, classic monolithic scaling.
Exactly. But now the slices are a few atoms wide. So instead of slicing thinner, we're having to learn how to stack entire pizza towers and deliver them at the speed of light.
Which is such a crazy paradigm shift. It's not just about making your smartphone faster anymore. It is a complete architectural shift in how human beings process information. We are moving from component-level shrinking to system-level gains.
Let's talk about the brutal physics of why we have to make that shift. Because 10 or 15 years ago, you had the gate of a transistor, and it easily controlled the flow of electrons, right?
It acted like a physical wall.
But at 2 nanometers, that gate is so incredibly thin that classic electrodynamics just get thrown out the window.
Completely thrown out of the car. I mean, when we say 2 nanometers, you have to picture the actual crystalline structure of silicon. A single atom is about 0.2 nanometers across.
So we were talking about a physical feature that is, what, 10 atoms wide?
Maybe 8 to 10 atoms, yeah. And at that scale, you hit the ultimate hard stop, quantum tunneling.
This is the part that just melted my brain. The idea that electrons are literally teleporting through solid walls inside the phone in my pocket.
Right, because of Heisenberg's uncertainty principle. At the subatomic level, an electron isn't just a tiny billiard ball sitting in one physical spot. It exists as a wave of probabilities.
Wait, so when the gate holding the electrons back gets whittled down to 5 or 6 atoms thick, what happens to that wave?
The probability wave function physically extends past the barrier.
Whoa, so it doesn't even need the energy to jump over the wall.
Exactly. The math just dictates that there's a statistical probability the electron already exists on the other side of the wall, so it just appears there.
Holy shit. That is wild.
It is. It's called subthreshold leakage. The transistor is supposed to be powered off, sitting at a 0, but current is just constantly leaking through it anyway.
And if you multiply that leakage by the 50 billion transistors packed onto a modern GPU,
you get a massive problem. The chip is constantly bleeding power, even when it's idle, and all that leaked power instantly turns into heat.
which kills Dennard's scaling, right? That old rule that said you could pack more transistors in without the chip getting hotter.
Oh, Dennard scaling has been dead for years. The heat density of modern logic cores is literally approaching the heat density of a nuclear reactor core.
Damn. You can really feel how hard the engineers are wrestling with this when you look at the TSMC and Intel roadmaps. They abandoned flat transistors completely. They moved to FinFETs, where the silicon stood up like a shark fin so the gate could grab it on 3 sides.
But even FinFETs are officially dead at 2 nanometers. The physics are just too brutal.
So now we have gate-all-around transistors. Intel calls them ribbon FETs. And the process of making these sounds impossible.
It's an absolute nightmare. They have to slice the silicon into these microscopic ribbons, stack them, and wrap the gate around all 4 sides.
Just to physically surround the electron flow and stop the quantum tunneling.
Right. And to do that, you have to etch away materials with atomic precision underneath these suspended bridges of silicon. Bridges that are so fragile they would shatter if you basically looked at them wrong.
And they have to do it flawlessly billions of times on a single piece of silicon.
Which brings me to the other wall we're hitting. The flashlights we use to draw these transistors.
Oh, man. ASML.
Yes. I want to talk about ASML and extreme ultraviolet lithography. Because reading about how we physically print a 2 nanometer chip made me laugh out loud. It's just absurd.
It literally sounds like
Oh.
science fiction written by a madman. Seriously. Because you can't use visible light to draw lines this small. The wavelength is too fat. It would be like trying to paint the Mona Lisa with a push broom.
That's a great way to put it. You need 13.5 nanometer light. Extreme ultraviolet.
But to get that light, you can't just flip a switch on a bulb. You literally have to vaporize metal.
Molten tin, specifically.
Right. You take a microscopic droplet of liquid tin and you shoot it through a vacuum chamber. And while it's in midair, you hit it with a high-power carbon dioxide laser.
Which just flattens it out.
Exactly. It flattens it into a pancake. And then, a microsecond later, a second, vastly more powerful laser blasts that pancake and vaporizes it into a plasma.
A plasma that is roughly 40 times hotter than the surface of the sun.
Holy shit. And this machine is doing this, what, 50,000 times a second?
50,000 times a second, just to generate the light source.
And because EUV light is absorbed by everything, even the air, you can't use glass lenses. You have to bounce it off mirrors in a hard vacuum.
And those mirrors are the flattest surfaces ever manufactured by humans. If you blew one up to the size of the Earth, the tallest mountain on it would be the thickness of a human hair.
Whoa. Just whoa. But this is where the brutal cost curves come in. Because these high-NA EUV machines from ASML cost upwards of $350 million each.
And they need 3 Boeing 747s just to ship one system.
I mean, if the physics are this brutal and the cost curves are this steep, at what point does it become financially impossible to shrink things further?
Well, we are basically there. A modern fab costs $20 to $30 billion to build. The economic half of Moore's law that computing costs would have every 2 years that has completely collapsed.
Which brings us to Jensen Huang's 2025 keynote. He gets on stage and says, Moore's law is dead, but we're not done yet.
It's such a massive pivot for NVIDIA. He's admitting that pure component-level shrinking is over. We have to pivot to system-level gains.
We have to stop agonizing over the puzzle pieces and rethink the whole puzzle. Because if you look at the 2026 roadmaps, everyone is explicitly moving away from monolithic dies.
Right. Building one giant perfect square of silicon is just too risky now.
Because of defect density. If you get one microscopic stray ion during a multi-month manufacturing process on a massive GPU,
you have to throw the entire $30,000 wafer in the trash. The yield rates are disastrous.
So instead of trying to mold one giant flawless castle, the industry is shifting to the chiplet era. It's literally like playing with Lego.
Heterogeneous integration.
Yeah. You carve up the architecture, you make one tiny perfect chiplet for logic, another for memory, and because they're small, your yield rate skyrockets.
Plus, you don't need your basic USB controllers built on a bleeding-edge 2-nanometer process. You can mix and match.
Why pay for aerospace-grade titanium when concrete does the job for the foundation?
Exactly. You save the brutally expensive 2-nanometer silicon just for the logic cores.
Okay, but this creates a massive new problem, the traffic jam. If you chop these components up, you have to push data between them.
And physical distance creates massive latency and power draw.
If you just put them on a standard green motherboard, the signals have to travel through centimeters of copper. At billions of cycles per second, a centimeter is a marathon.
And this introduces the villain of the whole chiplet paradigm, parasitic capacitance.
Right. I want to slow down and unpack this. How does parasitic capacitance bottleneck the data?
Well, when you push a pulse of electrons representing a binary one through a tiny copper wire, the copper resists the flow.
Okay. Basic electrical resistance.
But worse, those wires are packed close together. And structurally, 2 metal wires separated by an insulator accidentally creates a capacitor, a device that stores electrical charge.
Oh, wow. So before the data signal can even reach the other chiplet, the wire itself acts like a sponge and has to fill up with charge.
Exactly. The wire absorbs energy, and every time you switch from a 0 to a 1, you are constantly charging and discharging that parasitic capacitor.
That sounds like it would generate an insane amount of heat.
Immense heat. And it requires a huge amount of voltage. If the chiplets are far apart, moving the data can literally burn more power than the actual math calculation.
So the logistics of moving the data are harder than the math. That's crazy. How do they fix it?
Through advanced packaging, specifically TSMC's CoWoS technology, chip-on-wafer-on-substrate.
The tech powering the entire global AI boom. NVIDIA's GPUs wouldn't exist without it.
They absolutely wouldn't.
So instead of a rough fiberglass motherboard, TSMC developed the silicon interposer.
Right. They take a piece of raw silicon, perfectly flat, and etch ultra-dense microscopic copper wiring into it.
And this highway system sits underneath the chiplets.
Exactly. The chiplets are flipped upside down and bonded to the interposer with tiny micro bumps of solder. They sit just fractions of a millimeter apart.
So the physical distance is so short that the latency disappears.
Hmm.
The software treats 5 different chiplets like one massive piece of silicon.
It's the ultimate sleight of hand. You get the cheap manufacturing of small chips, but the performance of a giant one.
But the Nature papers point out that even CoWoS runs out of 2D real estate eventually.
Right, you run out of horizontal space on the interposer.
So the only direction left to build is up. 3D integration. Stacking chiplets directly on top of each other.
This is where the structural engineering just goes off the rails.
Seriously.
Ah.
I mean, it's like we've been widening the highway forever, and now we're suddenly building skyscrapers out of silicon. But if you stack a memory cache directly on top of a logic core, how do they talk? You can't run wires around the outside.
No, you have to go straight through the floorboards, using through silicon vias or TSVs.
Microscopic elevator shafts.
That is the perfect analogy. They use deep reactive ion etching to drill perfectly vertical shafts through the crystal structure of the chip.
But wait, silicon is brittle. It's basically glass.
Exactly. So first they have to grind the silicon wafer down until it is absurdly thin, like 50 micrometers thick.
Holy shit.
Yeah, at that thickness, a 12-inch wafer loses all rigidity. It just flops around like a wet piece of paper.
I'm over here struggling to plug in my charger without breaking the cable, and they are handling microscopic, wet, paper-thin glass.
Right. And then they drill millions of holes through it, line them, and fill them with electroplated copper.
So the memory chip on the roof can drop data straight down the elevator shafts to the logic cores below.
But filling silicon with copper pillars creates a catastrophic new issue: thermomechanical stress.
Because copper and silicon react to heat differently, right?
Yes. Coefficient of thermal expansion. The copper wants to expand way more than the silicon when it gets hot. If it's not perfect, the copper will literally crack the silicon from the inside out.
Like freezing water in a glass bottle.
Exactly. The expansion just shatters the whole thing.
And even if it doesn't shatter, you still have to deal with the thermal nightmare of stacking hot logic cores.
It's like building a high-rise without ventilation. The core on the bottom floor is trapped. It has no surface area to attach a cooling fan. And the core on the second floor is actively baking it from above.
Yeah. The thermal density just compounds.
The IE papers show teams experimenting with microfluidic cooling, etching microscopic plumbing directly into the silicon lattice to pump liquid coolant through the middle of the chip stack.
They are building microscopic radiators inside the crystal. That is insane. And wait, speaking of crowding, the Intel roadmap talks about backside power delivery, power via.
BSPDN. This is one of the most elegant re-engineerings of a microchip in decades.
Because traditionally, chips are a mess. You have transistors at the bottom and then 15 layers of copper wiring piled on top, handling both the data signals and the electrical power.
Right. The traffic grid and the power grid share the same cramped space.
And the thick power lines create electrical noise that messes with the data, plus the power loses voltage as it travels down through 15 layers of metal.
Voltage droop. By the time it hits the transistor, it's exhausted.
So Intel's power via just turns the whole thing upside down.
They completely divorce the power from the data. They build the transistors, put the data wires on top, and then physically flip the wafer over.
They grind away the backend, build a massive power grid on the bottom.
Backside power. It comes straight up into the transistor, and data goes out the top. It cleans up the routing instantly.
Every single one of these things, ribbon FETs, CoWoS, 3D TSVs, backside power, they're brilliant, but they feel so brute force. We are wrestling with extreme heat and fragile glass just to push electrons around.
Which brings us to the tipping point. Copper has reached its physical limit.
Section 3 of the roadmaps. The Silicon Photonics Revolution.
This is where we leave electrons behind.
When I first grasped this, it was a massive whoa moment. We know fiber optics for the internet, but replacing microscopic wires inside a processor with literal beams of light.
It sounds impossible.
I mean, let's unpack this. A computer speaks an electrical charge, ones and zeros. How do you tell a silicon chip to speak in lasers?
Well, the actual math, the computation, still happens electrically. The transistors push electrons. But the transport of that data across the motherboard transitions to the optical domain.
So an electrical one leaves the core. Where does it go?
It hits an optical transceiver. The heart of it is a laser diode shining a continuous beam of light. But a steady beam doesn't carry data. You have to blink it.
But you can't turn a laser on and off billions of times a second without burning it out.
Right, so the laser stays on. Instead, you run the light through a Mach-Zehnder modulator.
I love that name, Mach-Zehnder.
Yeah.
How does it turn a steady beam into binary code?
Wave interference. The laser hits a microscopic splitter and divides into two identical parallel paths of silicon waveguide.
Two identical light waves traveling side by side.
Now you take that electrical one from the processor and apply it as a voltage across just one of those silicon arms.
Because of the electro-optic effect. Applying an electric field to silicon actually changes its refractive index.
Exactly. It changes how light behaves. It slows down the light wave in that one arm, throwing it out of phase with the other arm.
Oh, this is brilliant. So when they merge back together,
If there's no voltage applied, they meet perfectly in sync. A bright flash. A 1. But if you applied voltage, the slowed down wave arrives out of sync. The peak meets the trough.
destructive interference, they annihilate each other.
The result is darkness. A 0. So the Mach-Zehnder modulator creates shadows out of bright beams, manipulating the phase 100 billion times a second.
Damn. They're literally replacing electricity with light. Holy shit.
It's incredibly elegant.
So these flashes of light, these photons, they speed across the chip in glass waveguides and hit a photodetector.
Usually made of germanium. It absorbs the photons, knocks electrons loose, and translates it perfectly back into electricity for the next chip.
And the big victory here is defeating parasitic capacitance. Photons have zero mass and no electrical charge.
Exactly. No electrical resistance, no heat generation in the waveguide, and you don't have to charge up the wire.
A photon enters one end and exits the other with almost zero energy loss, whether it goes a millimeter or a kilometer.
It completely shatters the fundamental bottleneck of data centers.
But wait, it gets crazier. Wavelength division multiplexing, WDM.
This is where optics completely embarrass copper.
Right, because with a copper wire, you can only send one signal at a time. If you send two, the voltages mix and corrupt.
But light has colors, wavelengths. You can have a red laser, a blue laser, and a green laser.
You pulse data onto all three colors and fire them all down the exact same microscopic waveguide at the exact same time.
And they don't interfere, they just pass right through each other like ghosts.
It's like turning a one-lane dirt road into a multi-dimensional superhighway, taking up the exact same physical space.
It increases bandwidth density by orders of magnitude.
But the engineering challenges. Integrating optics directly onto silicon is a nightmare, because pure silicon is a terrible light emitter.
It has an indirect band gap. When an electron drops energy levels in silicon, it releases a phonon, heat, not a photon.
So you can't build a laser out of silicon. Where do the lasers come from?
Direct band gap materials, 3V semiconductors, like indium phosphide. They are fantastic at emitting light, but bonding them to silicon is hard because their crystal structures don't match.
They don't play nice when they heat up.
Right, so engineers use heterogeneous integration to bond them at the atomic level. Which brings us to the holy grail, co-packaged optics, or CPO.
Historically, if a server needed to talk via fiber optics, the signal had to travel across 8 inches of copper motherboard to a bulky plug-in module on the front panel.
Which burned massive amounts of power.
So co-packaged optics just shrinks that whole module and moves it right next to the processor.
It puts the optical engine directly onto the CoWoS interposer. The electrical signal barely travels a millimeter before it becomes light.
But the physical alignment for CPO sounds maddening. You have to take a glass fiber thinner than a hair and physically bond it to the silicon die.
And the laser beam has to perfectly enter the core of that glass. If it's off by a fraction of a micrometer, the light hits the cladding and the signal scatters.
And you have to guarantee that alignment holds steady inside a vibrating server rack, heating up to 90 degrees Celsius.
Thermal expansion is the absolute enemy of optics. They have to etch microscopic V-grooves into the silicon to perfectly cradle the fibers.
And the urgency behind this brings us back to Jensen Huang. Why spend billions replacing copper with light? It's for the survival of AI.
Exactly. Large language models are growing at a terrifying rate, trillions of parameters.
Yeah.
You can't train that on one GPU.
You slice the model up across tens of thousands of GPUs working in parallel.
And they have to constantly talk to each other to update their mathematical weights. The network fabric is the bottleneck.
If you tried to wire a next-gen AI cluster with copper, the capacitance would require so much voltage that the cables would literally melt.
You'd need a dedicated nuclear reactor just for the network switches. Photonics is not optional. It is a hard physical necessity to scale AI intelligence.
So bringing this all together, the sheer scope of these roadmaps is staggering. The era of comfortable 2D transistor shrinking is over. The physics of 2 nanometers are just too brutal.
Classic scaling hit a wall.
So we chopped the chips into high-yield chiplets. We built ultra-dense CoWoS interposers to stitch them back together.
We moved into the third dimension, drilling elevator shafts to stack logic vertically, wrestling with thermal densities and backside power grids.
And when copper resistance became too much, we built Mach-Zehnder modulators to translate electrons into photons, shooting data at the speed of light.
We are watching the substrate of computation mutate into a 3D heterogeneous optical cityscape.
But looking past 2026, the documents hint that even this is just a stepping stone.
They have to be. Ultimately, the battle we are fighting here is for energy. As AI models scale, data center energy will become the hard limit on machine intelligence, not the silicon itself.
And speaking of what comes after these new paradigms,
Yeah,
we've been digging into even bigger shifts in energy and compute.
that's going to be massive.
Exactly. We're diving deep into that soon, so stay tuned. But for now, consider this final thought. For 60 years, Moore's law was invisible. The hardware abstracted the physics away, and software devs just wrote code that magically ran faster.
The hardware hid the complexity.
But that abstraction layer is collapsing. If future processors are split into chiplets, stacked vertically, and communicating via light, how will software have to mutate? You can't run linear 1990s code on a 3D, light-pulsing, asymmetric architecture.
Software optimization won't be about logic anymore. It will be about the physical topography of the data.
Whew, that was a lot. Moore's law may be changing form, but the quest for more performance is far from over.
Which future direction excites you most? Photonics, 3D stacking, or something else?
We'll see you in the next deep dive. Until then, stay curious and take care.